direction of gravity. Now, you're in outer space. You're going to play Captain Kirk. And you're in a space station, and there is no gravity. So, we're going to make some gravity for you. We're going to create some artificial gravity. So let this be your space station. It's a big wheel, a radius of about 100 meters. And we'll make it very fancy for you. We'll make some corridors around, like here. We'll make it a very interesting space station, like so, and like so. And this is rotating around with angular velocity omega. You're here. There you are. You go around. Therefore, non-negotiable, you're going around with a certain velocity v. This v equals omega r. And therefore, you require a centripetal acceleration towards the center. That is non-negotiable. Where do you get it from? Well, the floor, this is your floor, is pushing on you. Simple as that. Just like the floor is pushing on me now. This floor is pushing. There's nothing wrong with that. I don't fall over. And so I say to you, in what direction do you perceive gravity? And you say, this is the direction of gravity. Which is as real for you as it can be. Someone else is standing here. What do you think that person will think if I ask that person, what is the direction of gravity? Exactly. Radially outwards, opposing the push from the floor. So we could now calculate how fast we have to rotate this spaceship to mimic the gravitational acceleration on Earth, which is 9.8 meters per second square. Let's call that 10, just to round it off a little. So we want the people who walk around in this corridor to have an acceleration omega square r, which is about 10. So omega squared is about 0.1. So omega is about 0.3 radians per second. And so the period to go around is about 2 pi divided by omega, and that is about 20 seconds. And the tangential speed, that value for v, which is omega r, would then be 0.3 times 100, would be about 30 meters per second. Just to give you an idea for these numbers, which are by no means so ridiculous. What is interesting, that the perceived gravity, and therefore the centripetal acceleration, is 0 here. There is nothing. There is no gravity there. And so that may be a good place for you to have your sleeping quarters. Now comes an interesting question. You can walk around here without any problem. Could you walk into these spokes? So when you were here, could you then walk towards your sleeping quarters? So you're standing here, and I first ask you, in what direction is gravity? And you will say, well, gravity is in this direction. Can you now walk to your sleeping quarters? And what's the answer? You cannot. You cannot walk up against gravity. It would be like asking you to walk to the ceiling. How do you do that? An elevator or a staircase, that's fine. Because then you get the push from the stairs when you step on the stairs. So you could have a staircase here, and that's the way this person could go here. But you cannot simply walk here, because gravity is always in this direction. Now let's suppose you are at your sleeping quarters, and you wake up in the morning, and you decide to go back, either in this direction, or this direction, or this direction, or that direction. Doesn't matter. Could you do that just by going into this corridor and slowly, carefully starting moving, what would happen? Yeah?
You would fly out.
You would fly out. It would be suicide. Because the moment that you are here, already you have maybe not a very large gravitational experience, but already it's beginning to grow on you. The farther out you are, the stronger it will be. By the time you're here, it's 10 meters per second square. Remember, we had 10 meters per second square because we wanted to mimic the Earth. And so you literally crash. It's like falling into a shaft, jumping into a shaft. It's not quite the same because you start off with no pull on you. The moment you start going, however, the situation gets out of hand, and indeed, you will slam. So you can use the same elevator. You can use